Hey folks, Quilly18 here, and welcome to a Unity introduction to shaders, a practical introduction really, because if you are like me, shaders might seem like the sort of thing you'd really like to get into, but it can be very intimidating because it works quite a bit differently than a lot of other programming you're used to. And there's plenty of references online, but where do you get started? So what I'm hoping to do here is to work through a couple of practical examples of very simple shaders, just get your mind in place for understanding the workflow, and then you can use your personal superior art skills and math skills and different things like that, start looking up some references and come up with some really cool stuff, probably stuff that's a lot cooler than I can do. So what's a shader? Well, I've gone ahead and set up a simple little scene in Unity here. I've got 3 cubes. One of them is this god-awful shade of pink. What's going on there? Well, a pink color there, it represents some sort of error with a material in Unity. Let's look at what it is. This big cube is cube number 2. So actually, let me get rid of this box collider. We don't need that. Box collider is only there for physics, of course. To show something on screen, that thing has to be rendered in some way. And for a 3D object, you use a mesh renderer. A mesh is your geometric information, right? The vertices and triangles that make up an object. And a mesh renderer actually requires that you have a mesh filter. The mesh filter actually has the information about the mesh. It says, oh, this cube has 8 vertices, and it has a 12 triangles, and these triangles use these vertices in a certain way. Plus we've got normals information, different things like that. So that's what the mesh contains information is. And the renderer is responsible for shipping this mesh to the video card, but also combining this mesh with some sort of material. So the video card is going to get this set of vertices and be like, great, I've got some vertices. How do you actually want me to show these vertices on screen? And that's where the material comes in. And this cube doesn't have a material, which is why it's got this error. So let's go ahead, click this little button here, and I'm just going to give it the default material. This is normally when you make an object in Unity, it automatically assigns this default diffuse material. And of course, this should look very familiar to you. We've got 3 cubes on a plane, done. It's got shadows and stuff like that. It's got lighting, right? If we move around here, depending on how we are orientating ourselves compared to the light, the cubes will look a little bit different. Or we can take this light and rotate it around. Well, the material is responsible for the color of the cube, the texture as well, which we will do shortly, right? If you've got an image texture, the material is responsible for showing that on the cube. And the material is also responsible for looking at all the lights in your scene and using that to inform how it should be rendered. For example, if our light currently is on the other side of our cubes, then the faces, the triangles that are being rendered are not going to be very brightly lit. They're only going to use the actual color of the material plus whatever ambient light has been set up. And you can't set your ambient light to be 0. It would be purely black over here because there would be no light shining on it. Whereas if we go ahead and rotate the light this way, then the light is shining directly on the surface of the cube. So now our material is using this lighting information multiplied by, the color and the texture of the cube and, bump mapping and anything else you decide to throw in to generate the final color of the pixel that will appear on the monitor. All right, fair enough. You've probably worked with materials before. Let's go ahead and create a material. So we're going to go and just create a new material. I'm going to call this red material. Excellent. And I'm going to go and just change its albedo over here because this is Unity 5. The default material is a physically based rendering material, physically based shader, so it's got slightly different terms. So basically the albedo is the basic color of the object, so we're going to say it's red, and we're going to take our cube number 2 is at the front here, and I'm going to drop in the red material, and there it is, so it shows up red. Great. We could also, we could specify some sort of a texture over here. I could use my noise texture if I wanted, put it in there, and I could leave it white or whatever. So there's some sort of, it's combining the texture color with like the color from the texture itself multiplied by this color that we're specifying here to tint the color. And, great, fine. It's got a bunch of other properties. Awesome. Well, one thing you may have played with before is this little pull down at the top where you get to select the shader. So the material, you think, it's common to assume the material is what causes the object to look a certain way. Well, really, in a very real sense, the material in Unity is simply this screen here. It's this inspector. The material is the interface by which you use a user interface to send information to a shader. And the shader is the thing that actually does the work. So by default, this red material, this new material we created, is using the standard shader. But there's a lot of different ones in here. And they are used commonly for a few different things. Most of your objects in Unity may just use a standard shader or a custom one that you've written. Although, user interface stuff mostly uses these sprite or UI elements, right? Let's say I go and create a new 2D object, so a new sprite, it has a slight, it still has to be rendered on the screen somehow. So this uses a sprite render instead, which just uses different rules to tell Unity how to produce this image on the screen, but it still needs a material, and it defaults this sprite default one. If we were to go and create a user interface with either an image or text, it also has a material slot. Now here, it doesn't set one by default. We do have the image, it's in the middle of our screen here. If I go in like this, and then grab that. So there we go. It's a little hard to see because it's just a white square. I guess I could, there we go, throw this image in here. Boop, there we go. So now you can see it a little bit better. This still has a material. It defaults. It doesn't actually show it here, but all your UI elements will default to UI default over here, for example. So yeah, so everything that's got to be rendered in SimScreen has a material, which really is just a front end to a shader. And a shader is the program that runs on the graphic card to tell it how the pixels of this object should be shown on the actual monitor in the end. And there are, I'm trying to think of the best way to describe how many variants of shaders there are, because in a sense, they're all the same. Okay, but you'll hear references to vert shaders, or vortex shaders, I suppose. Vertex shaders, fragment shaders, surface shaders, post-processing, image effect shaders, and so on and so forth. And really, they're all kind of sort of the same thing. So we're just going to focus on specifically the vertex and fragment shaders. And actually, we're going to start off with the fragment shader example here, because it should be the most, I think it'll be relatively easy to deal with. So I will say this, surface shaders are sort of just a Unity kind of shortcut or macro to more easily pad out a frag/vert shader without having to do as much work. A surface shader basically deals with all the lighting information for you. So things like shadows and looking at all the lights in a scene and deciding how those lights affect your particular object that you're trying to render right now. The surface shaders basically do all that work for you, as opposed to having to write your own little lighting code. But if you want to do something that is kind of uses the lighting in a really funky way, like maybe some toon shaders or something like that, maybe you'll want to write your own lighting code in vert and frag shaders. Although frequently, the places where you'll use vert and frag shaders are places where you don't care about the lighting. Either lighting's already been handled, or you're working with an object that doesn't care about light by itself. If you really care about light, then you might use the surf. Anyway, I'm sort of getting a little bit beyond here. Let's do some work. So for our very first example, let me go and hide the canvas. We don't need this here. And this sprite, I'm just going to get rid of it. I'm going to keep working on this scene right over here. So what we're going to do first is we're going to apply a full screen effect. And what's nice about this is the shader that we're going to use for this full screen effect is not going to be attached to an object, so it doesn't care about the object itself. It doesn't really have any vertices to manipulate. It's going to be a pure frag shader, pure fragment shader. So how are we going to progress for this? We're going to create, first I'm going to create a new shader, and I'm going to attach a material to it. So I'm going to create a shader. Now, again, here we've got a variety of templates. These are what these are, these 4 templates. And let's ignore the compute shader completely. And I already told you, whoops, that the surface shader is basically a subset of a vertex plus fragment shader, more or less. So really we sort of have 2 left now. An unlit shader, that's basically your default, I don't do anything fancy, vertex fragment shader. That's as close to sort of an empty shader as you can get for your typical production. But the image effect shader is almost exactly the same thing. This is just one that is configured a little bit more closely to what you want for a full screen image effect, which is what we're going to do here. I'm going to have an effect that I'm going to attach to the camera. It's not going to be attached to any particular object. It's going to change the way the entire scene is rendered by being attached to the camera. So we're going to use this image effect shader. And all we're going to do with this thing is we're going to make things more red or something like that. I'll just call it a post effect shader. So the idea with this is the whole scene gets rendered in a way that in perfectly normal way. But what happens when your video card renders a scene? It basically creates an image. In the end, that's what it's showing on your monitor. It's rendering the whole screen for this frame, putting that all in an image, and then sending that image to your monitor or, within this window box over here. And this image is what we're seeing. It just so happens that this image is being updated, 30, 60, whatever frames per second. And that's fine. But what we're going to do is before sending this image to the screen, we're going to pass it through a shader. And we can do that because in this case, you can think of it, it's almost like we have a single object. Imagine our whole scene is a single quad that is perfectly aligned with the camera, and this quad just happens to have a texture on it. Well, that's exactly what this is going to do. It's basically this texture that we're going to be modifying with the shader is just going to be the final image. And then we can just muck around with it a little bit. It's going to be, I think, a really good way to introduce this. So we're going to call this post effect shader, and we're going to go ahead and open this up. Now, by default, it already sets up a few things for us. Let's embiggen this, and let's hit OK. Now, at the top here, this is the name of the shader. This is a hint to Unity about how to organize. In fact, the only place the shader actually does any work is between the CG program line all the way down to the NCG program, or sorry, just NCG line. This is where all the work of the shader happens. Everything else is just extra Unity stuff, basically, to help it understand how to interact with the shader, including the name. Now, by default, this hidden one is sort of a special one where it won't show up in the menu. And what do I mean by that? If we go and check, our red material, actually, it's not red anymore. So for the sake of argument, let's go ahead and make it red again, so that makes sense with his name. See this list of shaders? Notice there's no folder here for hidden. But if I go and rename this to something like custom, and then go here, you see we've got a custom folder with post effect shader. It's the one we just created. So this is just, where to put it in that menu. And then properties. This is how we interact with things. So let's go ahead actually and demonstrate that very well. We're going to create a new material because Unity you can't just use a shader directly. I mean, you can in code, but let's ignore that. And let's assume that the best way to get things done is with a material. So we're going to call this the post effect material. And we're going to tell it that it should be using this shader. And this shader only has one parameter. It's called texture over here. And that should make sense, or one property. That should make sense. Can we do more stuff? Sure. I mean, first of all, I can rename this. I could rename this to main texture. Now all of a sudden it'll say main texture instead of texture. Great. That's just a visual sort of thing. We could take in a color. We can do a whole slew of different things if we would like. I think what I'm going to do is I'm going to go ahead and just skip this for now. We're going to come back and do some more work with these properties later on. So let's leave this properties blank. Let's go look at the actual work. So there's a bunch of things going on here. Two of the important bits are these pragma lines, which could actually be combined together, I'm pretty sure. I think we can do this. Let's see if I'm lying to you. Oh, apparently I'm lying to you. We need separate lines for that? Really? I thought we could combo that together. I guess I'm just thinking of other things with like the surface shaders. All right, so we got both those lines. Now we don't get any more errors. Excellent. Okay, so we have this post effect shader over here, and it's defining. These pragmas are telling the sort of greater system, hey, we have a vertex shader here. It's a function called vert, and we have a fragment shader, and it's a function called frag. And if we look down, you can see we're including some sort of file. Okay, fine. We're defining a couple of structure types. Okay, fine. We're mostly going to gloss over this in our particular tutorial. You'll have to you can look at the reference material to figure out exactly what's going down there. But what we end up with are two functions down here: a vert function and a frag function. So effectively, this vert function will get called once for each vertice in the object that this shader is being applied to, right? So if this was a shader being applied to a cube, it would get run 8 times. I don't think I'm lying to you. I think it would do that. And then it gives you a chance to manipulate certain things based on these vertices. This is a good thing if you want to distort sort of more physically where an object is being rendered on the screen. We're going to be looking at this in an example a little bit later. Probably in the second part of this tutorial, I suspect, is going to be mostly based around messing around with the vert shader for us funkifying some font stuff, which is going to be fun to do. So mostly here, it allows you to take a look at your vertex information and to either manipulate them, or in these structures, you can add extra data over here. And that you can just, add some extra stuff. So let's say, we had another float 4 here, and we can look at this data structure in a bit, called foo. And it's not linked to anything necessarily, and we can just pad that in. We're not going to do that right now. But you can use that, you can fill in this data here, and then you sort of save it for another step. And then down here, you got a fragment shader. This fragment shader runs once for every pixel. That should be like, hold on, I got some red flags here. Let's do some quick math. If let's say, so this is going to be a full screen effect. That's what we're working on here. Now, this shader could certainly be for a tiny little object that's just off in the corner of the screen, and, only needs like 10 pixels to be rendered. But we're doing a full screen effect here. So let's assume if we are running at 1920 times 1080, that's over 2 million pixels. And this runs once for each one of those pixels? How fast or slow does this end up being? Because let me tell you something. Let's actually back up and go into Unity. The way that we're going to get this post effect to work, basically the way that this shader is going to be used on our full screen here is on our camera we're going to add a script. So I'm going to create a new C# script, and I'm going to call this, I guess, post effect script. There we go. That's going to be great. And we're just going to add that. Oh, come on. We're just going to add that to our camera, and then we're going to open this up. So on this script, we don't need a whole lot of stuff. This script, we can get rid of the start and update. It's going to have a function called onRenderImage, and it's going to take in 2 parameters. It's going to take in, they're both going to be render textures, and typically you call them source, render texture, and destination. That's the typical way of doing it. And basically what this is after our whole scene gets rendered, okay? So we've passed all our objects to the video card, they've all been rendered, and we've got that final image that is supposed to go to the video card. This is an in-between step where, so source is the fully rendered scene that you would normally send directly to the monitor. We are intercepting this so we can do a bit more work before passing it on. And to pass it on, we're basically just going to do graphics.blit. This is a function, and we're going to copy the source into the destination. And right now, we're going to do this directly. And in fact, if we do this and we run the program, assuming I haven't made any syntax errors, we hit play, nothing will happen. Everything is perfectly the same as before, because we're not actually intercepting things. But one could easily imagine for a situation. This is like pretending to do image effect in CPU here. This is just, do not do this. This would be really bad. We got to grab the pixels in some ways, right? We want to do some sort of image effect, and we're going to do it here in Unity code. Don't do this. It's terrible. So we need our pixels, which is really just an array of colors called pixels, and we have to get it in some way. There's a lot of different ways to do it. I mean, effectively, you're doing some sort of like texture.getPixels. Right? If you do this, this will fill in your array. We're just going to go ahead and we'll just instantiate some new ones. And we're going to instantiate 1920 by 1080, because we're like, let's say this is 1080p. You can ask Unity what your current resolution actually is, but for the sake of argument, we'll do this. Note, this is going to allocate over 2 million of these pixels, these color arrays. And each one of these is several bytes. So really this is going to be allocating, I don't know, 10, 20 megs of memory every single frame. And you can't really, as far as I know, I mean, you can't really just do this once and start, because I'm pretty sure that if you were to do texture.getPixels, I believe it allocates, it doesn't give you the raw pixels for you to mess around with. I think it allocates a copy of that array. So effectively, we would be assigning this memory every time. That may or may not be true, and there's probably lots of ways to optimize it, but just for the sake of argument. So we've got that, and then we've got some sort of a loop for int x. Actually, hold on, let me take the shortcut for tab. That's 1920, so this is x, and then for y is less than 1920, and then we change our pixel. We change pixels at position x plus y times 1080, and we set we set the red to be equal to some equation. We do a little bit of vector or float mathematics to slow things down, like that, and we do that, and then we apply it. Probably apply some kind of texture.setPixels with pixels in there. And then there we go. So again, sort of a contrived example. How fast would this run? So this script is already applied to the camera, and it's a script that does a whole lot of nothing. but it is going to just sit here and kill a little bit of our CPU time. Double the float. Oh, let's specify that those are floating point things. That should get rid of the error. Excellent. Let's hit this little window here to get our stats, and let's hit play. How's our frame rate? All right, we're sitting somewhere around 45 frames per second right now. In a scene that does nothing, absolutely nothing. It is a dead scene, and we're only running that fast. And we're also allocating, deallocating a lot of memory. So we're actually getting lucky here. This could have been way worse. In fact, I don't know what I did slightly differently here. Oh, I think, let's say we did like a little bit more complicated math. Let's say we needed a square root. I think that was my, whoa, that was my example. Or not a square root, just a power function. Square root would be even slower. But I think if we needed a power function, so that to the power of something else, now I bet you would get really, really abysmally bad rates. Yay, 5 frames per second! Just by taking a power function of something. 5 FPS. Listen, even if you're a console gamer, that starts to feel pretty slow, considering the scene does absolutely nothing. And there's lots of examples why we might need to do some more mathematics to figure things out. What if you're trying to do some sort of distortion in your screen based on, distance from, like, in a circle? And so, like, all of a sudden, well, you need to use the Pythagorean formula and different things like that. Well, then you need power and square roots in these things. And oh my God, turns out when you're trying to do 2 million of something in a frame, it slows you down really fast. But isn't that, so this we don't want to do because like really bad in CPU, but isn't that still exactly what we want to do here? Right now, this shader is just inverting the color, but it's really easy to assume like we could start doing some sort of math here. Let's do some dummy math in here. Let's say we're going to create a new float called A, which is, I'm going to try to like intentionally make it even more unoptimized here. Another float called B, which is this, and a float C, which is A times B, and then, is it just power? Hold on. Shader pow. It's just pow and then 2 numbers, right? Yeah, okay. So then we have a float D, which is power of, let's say, A to the power of C. I think this is all valid code. Let's go and find out. Excellent. Yes. Okay. So we got no errors. So I've got some sort of valid code here. Now we're still not using this shader yet. We're still not using this shader yet. How do we actually use it? Okay, well, in our post effect script, we're copying the source into the destination right now and doing nothing else with it. What we'd like to do is during this copy, we would like to pass it through a material, through a shader to use a sort of a filter effect, right? Like an Instagram filter. That's what we're doing. So as it turns out, this graphics.blit function can take a third parameter. Actually, it's got a few different variants, but it can take a third parameter, which is a material. Now, you can use this graphics.blit even without render textures. You can use a normal texture. Oh, by the way, if you've ever tried to follow any sort of tutorial before that used shaders and particularly do these post effects, you might have seen time and time again that you can't do this in the free Unity version. That is no longer true. As of Unity, I think 5, ever since the Unity free version, I think, started getting called the Personal Edition or something like that, this on-render image, graphic.blitz, render textures, all these things we didn't used to be available in the free version is now available. You can do this in the free version. In fact, I'm working in the free version here. Okay, so you can pass this copy step through some sort of material, which is what we're going to do. I'm going to go public material, material mat. And if we look at our main camera script over there, it wants a material, so we're going to grab the post effect material and feed it in there. Then I'm going to hit play. Excellent. This material, if you'll remember, we haven't actually looked at it, but this material, all it's doing is inverting color. We're going to look at this in a second. Right now, what this material is really doing is a whole bunch of useless math. How fast is this running? And remember, it's still doing this on every single pixel. How fast is it running? 90 frames per second. That sounds a lot better, doesn't it? Actually, it's even better than this. Because by default in Unity, project settings, quality, by default, VSync is turned on. So that it limits the frame rate to no faster than the refresh rate of your monitor. Let's turn that off for a moment here, which, will start to overwork my graphic card. But out of curiosity, how fast is our frame rate now if I hit play? Over 2,000 frames per second. We're doing exactly the same sort of math as before. A bunch of stupid math. You know, some random floating point equations, we're taking a power function, and yet instead of running at 5 frames per second, we're running at 2,000 frames per second because we have shifted all the work to the graphic card. And what the graphic card really is a whole bunch of tiny little CPUs. They're simple CPUs. They can't do a lot of stuff. They have limited memory, each one of these CPUs, but there are a lot of them that are working at the exact same time, and they're very fast. So each one of them is running this tiny little program that it gets run once for every single pixel, but it turns out to be insanely fast. That's the real advantage of shaders. You get to, because all the cool funky stuff that you can do with shader, you could do in a normal script that manipulates pixels, but it would be apocalyptically slow. Excellent. So it turns out this is really fast. So this fragment function that gets called once per pixel, what is it doing right now? Well, right now it's doing very little. It's got this function here, text2D. What it's doing is it's taking our texture. This is our main texture. If we look over here and we look at our cube, right? This is my red cube with this red material. Oh, that's not what we're using. That's right. We're not doing anything with it. Oh, dirt. So right now, sorry, my bad. It's taking in a main texture. And this material does have a main texture. This post-effect material does take in a slot for main texture. We haven't assigned one. We could assign a material, but if we hit play, you'll notice something. As soon as we start playing, this goes blank. Why is it? Well, because when you are using a material as a post-effect shader and calling it here, this material, the main texture, is being set to the source. So when we look at our shader script, this main texture is literally just the screen, is this, or more accurately, this. This is what comes in as the main texture. And then for every single pixel, and we're getting a coordinate, the UV coordinates, which if you've ever worked in a 3D design program, you've worked with maybe UV coordinates. This is our current coordinates. The I, this is our sort of input. In fact, a lot of code might write it like as something like in, and then we can say in.uv, right? This is our input information. So this contains the current coordinates of the pixel, basically, for this current mesh / texture and whatever. So we're saying, hey, this UV coordinate from this texture, get me that pixel there. And that's what it is. We're getting the color. COL here in this case is a color. And a color has 4 components: red, green, blue, and an alpha. And fixed 4 is one of the many sort of data types that you work in these languages. Fixed 4 is, unless I'm mistaken, a fixed in this context is a number that goes from basically -2 to +2, I think is the range. But really, our colors go from 0 to 1, right? If we had a color that was 0, 0, 0, that would be purely black, and a color that was 1, 1, 1, that would be purely white, and then anything in between is grays, or if you mismatch it so that you have a red of 1 and a green of 0 and a blue of 0, then it's just purely red, right? So it's got those 4, and the 4th value is the alpha, which is transparency, right? So this pixel information is just being represented by this data type. It doesn't have a specific data type for pixel info because it doesn't need one. It keeps everything a little bit simpler. But you can imagine that this is just pixel info. So it's getting the color from the texture at a certain coordinate. Then we're inverting the color. This is actually an operation that you couldn't just do in C#. You would instead have to do something like col.r equals 1 minus col.r. I mean, I shouldn't have to explain why this reverses, right? Because currently, let's say r is equal to 1, so 1 minus 1 would be 0, so we've inverted it, or vice versa. If our current col.r was 0, 1 minus 0 is 1, so again, we're inverting it. So typically, you might have to do something like this. But there's a bunch of little shortcuts to allow you to do this sort of operation, and it's great. This also works with vertices and stuff in the shader language. So we're just inverting the current color and then returning that. So we're getting the color from the texture and then returning that. What else could we do? Could we, instead of inverting it, let's just force the red portion of the color to be 1. What would that look like? So I'm going to switch over here, and I'm going to hit play. And the whole screen turns red, or pink, or whatever. Basically, we've turned the redness of each one of these pixels to 100%, while not touching the green or the blue. Hey, very cool. You know, it's kind of annoying to hit play every time we do this. Is there something we can do to avoid that? Yeah, absolutely. In any Unity script that is attached to any kind of object or whatever, you know, any mono behavior, you can give it a little function, a little thingy here that says execute in edit mode. If we do this, then your script will run in edit mode. On render image will be called. Also, any like void update will be called. I believe on start will also be called. I don't think fixed update gets called, but don't quote me on that. Look up the reference yourself. But definitely update does, and definitely on render image does. So now by doing this, this script will run in the editor, which means as soon as it recompiles that script, our shader, I don't have to hit play anymore. Our shader is now live. And if I make some changes to our shader, let's say I flip it back to inverting the colors instead of sending it red. I hit save. I just go over to Unity. It recompiles the shader, and instantly it's still running over here, so we get the new visual effect. And if I like take one of these cubes and rotate around, we can see everything in real time. Ah, very cool, very funky. Love it. Okay, very handy there. So already, this should give you a little something, something like, oh, okay, Fragment. All it does, its entire job, this function's entire job, is to tell the video card, basically, what color the pixel should be in this particular location. So you can screw around with the colors. That's one possibility. I like that. What else can you do? Well, instead of screwing around with the colors, so let's say I comment this out. So now we're just going to get the correct color from the texture and return that. So now everything will look normal, and it does. But what if we start to do something really weird? Like, what if we start to say, instead of grabbing the color at the correct pixel, what if we start to offset things? Let's give that a try. So right now, we are, this is where we're asking the main texture, hey, what's your pixel at this coordinate? What if we move this a little bit? So let's add an offset, which I believe this is a float 2. So let's offset it by, I don't know, 10 in the y direction and see what happens. What I'm going to do is save and switch back. Oh, oh right, of course, derp. Let's try and offset it by a small number, not 10. That's not even really visible. Let me try a couple of little other options. This might not be the best way to show the example. I thought it would be. Oh, there we go. Excellent. Excellent. So I've just got the script set to the other monitor, and what I've done here, so I'm setting it back to 0. So this is 0. I'm going to set it now to 0.1. This should raise the scene up by 10%. So I'm saving and I'm switching to Unity now. And that's exactly what happened. It raised the scene up by 10%. Because what we're doing is when we're grabbing the pixels from our texture, we're grabbing it at a y that is 10% higher. Because texture coordinates range from 0 to 1. Right? So if I'm adding an extra 0.1 to the y, then it's grabbing from pixels 10% higher up. Now there's a bit of an inversion here, because if you are grabbing, imagine this, our texture, if we're grabbing our texture from 10% higher in the texture for certain pixels, then wouldn't it reduce? Maybe it's not confusing to you at all, but there's a bit of an inversion in coordinates. So you might have assumed that having a positive number here would actually make the visuals go downwards. But anyway, so there, okay, now we can grab pixels from different area. Now, would we want all pixels to be moved together? Well, I mean, if you want your whole scene to move up and down, well, honestly, the easiest way to do that is probably just move your camera around, but I guess this is fine. Can you do something a little cooler here? Yeah. What if right now we're moving every single pixel in our picture up by 10%? What if instead of moving every single pixel the same amount, what if we move them a slightly different amount? How would we do that? Well, let's say, so this is the vertical movement, right? Like, well, let's keep the x at 0. So let's only move the y-axis. So we're only moving our pixels in the vertical direction. What if we move them in the vertical direction proportional to their position in the x-axis? Which we can do, because this input has like vertex. This is world space information. Actually, at this point, I guess it's been converted to screen space, which is fine. Okay, so if this is screen space, I think this will be in pixels. Let's see. We'll give it a try. Let's say we're going to move up and down in the y direction, right? Like, or, you know, that's UV coordinates, but basically we're moving up and down vertically here in terms of our texture, but we're doing it based on our x. And I think what we're going to want to do here is divide it by, I don't know, something like 300, something like that. We'll see what happens. And let's go and see what this does. Wow! So here it's normal. This is actually where the pixel is supposed to be. But as we move further x, we move higher up in the y. Obviously, we need to shrink this down even more. Let's try by 1,000. There we go. So we're distorting it this way. Interesting. Can we do something a little funkier? Well, what if, instead of just doing it sort of linearly like this, what if we feed it into a sine function? Right? Sine is a function that will take in a number. I believe these work in degrees in here. It might be radians, though. Actually, I don't remember if this scripting language or its programming languages uses radians or degrees here. But it doesn't matter. We're going to feed it in some sort of value, and it's going to return a value that goes from -1 to +1, right, as a sine wave. Let's see what this looks like. We'll probably have to tweak the numbers. Okay, yeah, we definitely have to tweak the numbers. Oh, well, first of all, because it's returning it from +1 to -1, obviously this is going to be way too pronounced of an effect. Let's divide it by like 50 or something like that for 1. Okay, that's probably not enough of an effect since I can't see it. By 10. Okay, now with it is starting to go up a bit here. But now let's go and make this even smaller. Something like that. Or the other way around. The other way around. Like this. Okay, and more. Divide by 50. Yeah, that makes sense. Ah, now, hey, that's kind of funky. Right? So, I mean, this is purely a visual effect. If we go and we grab, say, our cube over here. Let's get out a 2D view. Let's look straight down. And if I move this around, I mean, wow, that is pretty weird and awesome. So now you're like, you should be getting more ideas of like, okay, we can manipulate things. What if, now this is still relatively static. It looks particularly weird if we rotate the camera around. And you can see in the scene preview what it would normally look like down here. And you can clearly see how the sine wave is distorting all this stuff. We can also add a time parameter here. One of the bits of info that Unity passes to our shader is how much time has passed since the program started running. And we could say, add that to our little sine function. So basically, there is this time variable, this time property. This is actually an array. Well, it's actually a fixed, I think it's a float 4. This one, the 0th one, is actually the number of seconds divided by 20. 1 is the number of seconds. 2 is the number of seconds times 2. And the third one is the number of seconds times 3. I think it's times 3, not times 4. So if you just want the number of seconds, you could do that. And I suspect that this will be too fast. Too fast or too slow? Too fast, I think. Now, one thing is, even though our script is still running here in edit mode, the time will always be 0. The Unity will always send 0 as the time to the shader unless we're playing, since the time that the play started. Oh, actually, that works out pretty good. You might want to multiply that time to get this effect faster, or you might want to divide the time to get the effect slower. We could maybe go for a more sort of subtle, you are slightly drunk effect if we make the sine wave sort of less prominent. Oh, maybe even less than that. Let's say times 50. There we go. And then you go faster or slower. Maybe, you could go like quite slow. This would be a very, very, very subtle shift. In fact, if we make this number even bigger, so the sine waves is less of a thing, and it will be very, very slowly shifting over time, almost imperceptibly so. Okay, that may be a little too slow, but I kind of like the idea of just sort of screwing with the user a bit, Especially if you started off with it sort of 0, and then, yeah, there you go, sort of just distorting a little bit in the distance. Now that sine wave is still quite regular, right? You can tell that it's a waviness. Is there a way to make this distortion a little bit more random and a little less regular? Absolutely there is. What if we added a certain amount of randomness here? Well, two things. One, a pure random function doesn't really exist in the shader language. And there's lots of reasons for that. It probably has to do with concurrency and optimization, different things like that. You can sort of fake it by using a sort of a hash function and passing in x, y, and z coordinates and, sort of running it through some sort of mathematics so that you can end up with a number that feels pretty random, but a particular coordinate will always return the same amount, and that's not too bad. The final way of doing it is to use a source of randomness, a source of noise, which is what this texture is going to be for. And this will sort of act as a random seed for us. And what's going to be quite nice is we don't actually want like a total random distortion everywhere, because that's just going to be like weird noise that just shoots up and down randomly at every single pixel. And effectively, you're not going to have an image anymore. But a cloud image like this, which is very easy to make in basically any image editing program, I just did it in Photoshop. A cloud image like this gradually shifts from light to dark and back. And if we use this as a sort of source for this distortion, wouldn't that look kind of funky cool? In fact, it looks very funky cool. We're going to put a cut in here, but in the next episode, we're going to look at using this noise texture as a source for our distortion. And we're not going to use it on the full screen effect. We're going to end with the full screen effect at this point. And instead, we will start looking at another way to use shaders for 2D elements. Well, we can also use it for 3D, but instead of doing a full screen element, I'm going to show you a shader applied to a object instead of, well, effectively all objects simultaneously. But it's basically going to be a continuation of this work over here, and I think that the different example will prove it to be quite cool. So we're going to continue with fragment shaders a bit more next episode. And then we're also going to show, hopefully in the same one, we'll also show some use for the vertex shader. Going to be, again, relatively simple examples, hopefully just enough to get you started. Oh, one of the other things you can do is, okay, maybe not with the full screen shader, but you could take into account distance from the screen and apply more or less wobble that way. I think for that, you'd really want an object that exists in your scene and uses something called grab paths. Google that, grab paths. We don't have to use grab paths for a full screen effect because the current screen render is set to main text. But if we weren't doing a full screen effect, imagine that you had say a fish tank in the room and you want this sort of wobble. For anything that's behind the fish tank, you want it to end up kind of wobbly like this, but it's obviously not a full screen effect. It's just happening to things behind the fish tank. Well, the fish tank would have a material, a shader, that would have this logic, but instead of using main text, because here you can assume our main texture is just the whole screen. Instead, you do something called grab paths. So what it would do is it would render everything behind the fish tank first, save that in an image called grab texture, and then feed that to the fish tank as this grab texture parameter that you could then use to, add this sort of distorted image on top of your fish tank panel that would distort everything directly behind the fish tank, and then you would just go on your merry way doing extra stuff. So anyway, a few things to Google. Again, next episode, we're going to come back. We're going to do a little bit more with fragment shaders, and we're going to use these cool noise textures to make, I think, a really funky, cool effect. Thanks for watching, folks, and I'll see you next time.